Thanks, everyone. So my name is Rajesh Nishtala. I'm a software engineer at Meta. I'm currently one of our TLs in our AI infrastructure org. So I'm going to be talking a little bit about the infrastructure that goes behind large-scale training, a little bit of a glimpse of what we've done and where we're going, and how to get these large models trained. So as you guys already probably know, Llama is our open source large language model. It's designed for developers, researchers, and businesses to build, experiment, and responsibly scale large-scale generative AI. As Jan and Mark has said many times, we have a strong commitment to open source on this. But it's not just the model itself. We have an entire ecosystem and systems that are designed around Llama that are supportive to help the community grow, as well as a lot of safety tools to make sure that generative AI can be used responsibly. So now, Meta's been doing AI for a long time. If you've ever scrolled on newsfeed, used Instagram Reels, watched a Facebook ad, these are all coming through our AI products today. But prior to Llama, our largest jobs were just 128 node A100 GPU jobs. But within a few months in 2023, we realized that we needed to scale up from 1K to 2K to 4K and eventually to 16K GPUs. Our current runs are obviously much bigger than this. If you think about that scale, it's like planting a seed and growing into a mature tree within a year. There's two parts to this problem, though. First, we needed to build the physical infrastructure capable of hosting these large training jobs. If you've ever seen the data center pictures, it is insane how large these buildings are. And our next data centers are if you've seen the posters, are going to be about the size of half of Manhattan. These buildings are gigantic. Second, we needed to build new software systems and operations muscle to be able to use this capacity. This is a lot of capacity that we're deploying, and any wastage of that capacity is a lot of wasted money and resources. So let's talk about each of these in turn. We have our open compute infrastructure, right? So we've deployed we've talked about the type of hardware that we run, the network cards, and everything like that. So you can just go to the internet and download and check it out. And we have shared a lot of details about our scheduling and storage system. So we have our system called MAST, so I'd encourage you to look at that, as well as our storage systems called Tectonic. And finally, we've also shared our operations side a little bit. And I'll get to that in a few slides here. So in order to build out these large clusters, we first had to build out the physical data centers, right, where we host tens of thousands of GPUs within a single set of buildings. Performance is key, so we had to tune these GPUs to run at their maximal thermal power design, which is about 700 watts per H100. If you start multiplying the number of GPUs by the number of watts this takes, it's enough to power a small city and eventually bigger and bigger cities as the clusters get bigger. Concurrently, we also needed to figure out how we ramp up our InfiniBand and technologies to connect all of these clusters together in a high performance network. Now, as many of you know, the key tenet for Llama training is that we have to run these jobs on thousands of GPUs for weeks on end. It's not like a one-day worth of run, it's weeks on end. So during that time, as Dylan mentioned, failures happen all the time. And we have to figure out how to maximize the effective cluster utilization and not get caught off guard by failures. So we built our custom scheduler that does this stuff. And then, to maximize the capabilities of each of these GPUs, we first understood we built a scheduler to understand the capabilities of a GPU within a single machine, the machines within a rack, racks connected to interconnected into a small cluster, and then the larger training cluster itself. So now that we have this cluster, our next challenge was to figure out how to map the various levels of parallelism that Llama training has to occur to these various hierarchies in the system. So for example, if we wanted to do highly tensor parallel computation, we had to make sure that they map very closely to the GPUs that are close to each other. Now, and then as you go through the pipeline parallelism, data parallelism, we can afford to relax the connectivity constraints a little bit. Next, we have to make sure we focused on getting good use of our training cluster, right? Specifically, learn that a training job could stop due to a single failing GPU. Happens all the time. Network congestion or communication issues, or even just bugs in the software stack. So we had to we benefited from years of our production debugging experience in order to automatically find and fix these challenges that happened at scale. Now, one of the interesting takeaways from all of this experience is like going to sound a little mundane, but in order to actually scale training as well, the biggest investment that we made was actually in our debugging tooling. The ability to find a fault, understand what broke, and then quickly find and fix it. So these things really paid off, right? So if you look at our LLAMA 3 paper, we achieved over 90% plus effective training time using these machines, even in the face of failing GPUs, firmware upgrades, Linux kernel upgrades, and everything that we had to do. For the most of our failures are actually due to hardware faults and very little due to software failures. Now, as we continue to build all of these different things, we continue to harden these different components. So in our infrastructure, we have components for distributed checkpointing, data loading, logging and observability, and debugging tooling. So what's next? We want to look forward to drive down costs, more modalities, more longer context, and more agentic use cases. Now, as this community knows, we need to push beyond the bounds of pre-training on a fully synchronous stochastic gradient descent. Like we're starting to hit the limits of what a physical data center can contain, and we need to do more than that. So we have to span larger geographic distances, and we have to be more asynchronous. In addition, we also expect our the work to get a little bit more complex, right? It's not just going to be a single pre-training job, but it's going to be a lot of agentic behavior and things like that. Now, what can PyTorch do to enable this world? PyTorch, when we designed PyTorch in distributed context, it was designed in a context of fully synchronous SGD training. So we need to evolve the PyTorch programming model itself to go beyond this and support these new use cases. So until now, the primary mechanism for programming large-scale HPC jobs is running the same training script on multiple machines, the SPMD approach. This is pretty convenient because you take one program and then just stamp it into all the different hosts. And it's actually scales pretty naturally. You don't have to worry too much about how you dispatch work. And finally, it fits naturally into the how HPC and MPI and all these things that we've been working on for decades have fit into this. But this doesn't actually starting to work, right? As we continue to scale, some of the challenges of building large infra don't really lend itself to this style of computation. For example, infra is tightly coupled with the user code, so we can't actually figure out what broke when, right? It's a real pain to understand what if it's an infra failure or a user code failure. Second, if you look at the parallelism constructs that are required for training, like something like pipeline parallelism, this is the top is the pipeline schedule for our pipeline parallelism for LLAMA. The bottom is what's expressed in the Megatron paper. Good luck trying to express that with SPMD, and then debugging that with SPMD program. We have some of our best engineers take a long time to do this, and it was not easy. And one of the foundational challenges with the SPMD approach, is that you have a system where you know the global control flow, the data dependencies and things like that, but you turn it into a distributed consensus problem. So you've taken what should be a single control problem and turned it into a distributed consensus problem, and that makes your life a lot more complicated. So our solution is to go through what we call a single controller approach, right? So the idea is that we'll have a single controller that will issue commands to a device mesh. And the core idea is to leverage a programming model that can leverage the centralized control plane and decouple the model training code from how we manage the underlying accelerators. Users can refer to the cluster as a device mesh and control its lifecycle. Applications are written through a centralized controller with the individual operations that are then dispatched to a fleet of workers. With the single controller mechanism, a developer doesn't see their experience any different than running a cluster locally versus remotely. Now, rather than talking about it, and let me actually show you some code about how it works, right? So this is a simple pipeline parallelism example, right? So if I wanted to, let's say, take a tensor, I first initialize my device mesh. So I construct an 8-node job that has 2 GPUs per host and 4 hosts. Then we slice up that entire mesh into 4 different groups. And then let's just initialize our tensors on one of the sets of GPUs, right? Now with some interesting values, with 0 and 1. And then here comes the fun part. We're actually going to do a pipeline parallel computation where each set of hosts will take their value, add to it, and then pass it on to the next sequence in the mesh. And all of this done with these 4 lines of code right there, right? It's a pretty straightforward computation. And what's interesting that's happening here is that the controller understands the control flow between these different variables and the dependencies and says that I can actually orchestrate the communication underneath the covers to make this a reality. And once we reach the finish, we'll just, get the work and send it out. Now, this is the exact same code that does the exact same thing written with PyTorch distributed today. And you can see that in this example, which is, you can run this right now, is that we have to do some really fancy math about do my computation based on what rank I'm running. And look at all the sends and receives and the rank arithmetic that we're doing. Now, for a simple program like this, you could say, well, what's the benefit? But as programs get more complex, as we go from a few nodes to a few 100,000 nodes, the rank arithmetic gets really complicated, especially with even more complex sets of parallelisms. So, as we said, we are excited to dive deeper into the salient. The single controller mechanism has a global view of the system and creates a single coherent control plane. To test a large SPMD program, one of the advantages of this mechanism is you can actually have the driver of the code live on your dev server or your laptop or wherever and actually attach to a large cluster. Rather than deploying the same program in a different cluster, you can actually deploy and attach to a large cluster, which should be beneficial for developer experience. Because we're not having to match sends and receives and making sure everybody's in the same collective at the same time and all these kind of challenges, it should minimize deadlocks, which is obviously a big deal. And because a single controller mechanism is actually able to observe and inject the operations, we can fine-grainedly say when and where a GPU has failed, rather than waiting for timeouts and waiting for other kind of mechanisms to see what has happened. And finally, because we're actually issuing a sequence of operations, right, and not just an entire program, like a database bin log, right, from that life, you can actually potentially replay from checkpoints and get a specific host back to a specific state. Again, when you're training at very large scale, minutes and seconds will allow you to get higher cluster utilization because of the failure rate of these GPUs. As you can tell, we're pretty proud of how far we've come on large-scale training, but this is just the beginning. Thanks for the talk, and now I'll be around if you guys have any questions. Thank you so much.